Welcome back to our online students. Today what we're going to do is take a look at electrolytes and molecular and net ionic equations. So to get us started here, electrolytes. When I hear electrolytes, I think of these TV commercials where they have some athlete who's sweating and drinking some beverage that looks kind of like Kool-Aid and gives you the impression that they can just run faster and jump higher. And what's electrolytes? And you're like, I don't know, what are electrolytes? And some people will say, well, it's what they make Brawndo out of, because Brawndow's got electrolytes. But why does it have electrolytes? Because it's what plants crave. And you're scratching your head at this point. Well, you might have to Google that one. But electrolytes are really just when things dissolve in water and they form ions. That's the thing. So it dissolves in water and forms ions. These would be electrolytes. So now here we have different solutions on this slide. And the first slide just has water. Now, water dissolves in water. We call that an aqueous solution. No, we don't call it an aqueous solution. Bad. Okay. So if you just have water, it really doesn't dissolve into ions that much. Okay, just a very, very small amount, but not much. And so we don't consider water as an electrolyte. However, sodium chloride, when we put that in water, that dissolves into sodium ions and to chloride ions. And so that is an electrolyte. And electrolytes, the word electro gives you the impression that it conducts electricity. And yes, this is true. You can put wires into salt water and it should conduct electricity to some degree. Now that's different than solid sodium chloride. If you just take some table salt and stick some electrodes in there, not going to conduct electricity. So the trick is you have to have something dissolved in water that forms ions. Now there's other things that dissolve in water, like ethanol. Ethanol dissolves in water, but it doesn't dissociate into ions. So does sugar. Sugar dissolves in water, but doesn't dissociate into ions. So the big thing here, the takeaway, put a star next to it, is electrolytes must dissolve in water and form ions. Electrolytes must dissolve in water and form ions. Now, strong electrolytes, these are things that dissociate nearly 100%, so almost completely dissociate into ions. And examples of this are strong acids and strong bases. So I'm going to say here, let's see, electrolytes, let's see, dissociate in water to form ions. Okay, there's our definition. And then we have strong electrolytes. Strong electrolytes, these are things that 100% or nearly 100% dissociate in water to form ions. They conduct electricity. And examples of this would be things such as sodium chloride. And then we also have nitric acid. And what else do we have here? HCl. HCl, which is hydrochloric acid. And so we might also think of these as salts and then strong acids and bases. So salts that dissolve in water, strong acids, and strong bases that dissolve in water. These would be strong electrolytes. Strong electrolytes. Weak electrolytes, these are things that only partially dissociate in water, in which case they don't completely dissociate in water. They may dissolve in water, but they don't dissociate in water. And an example of this is acetic acid, also known as vinegar. And vinegar, when it gets into water, it only partially dissociates, and so it doesn't completely come apart. And this is partially why acetic acid is a weak acid. So weak electrolytes would be weak acids and bases. So let's hear weak. Weak electrolytes, this is going to be weak acids and bases. Weak acids and bases. So I'm just thinking like test type questions. If you were asked, would this conduct electricity? Would this not conduct electricity? Would this be a strong electrolyte? Would this be a weak electrolyte? Really what you need to be able to identify is something a strong acid or a base? Is it a weak acid or a base? Is it a salt that dissolves in water? These are the things really that we need to be able to identify. And there are some rules for this that we're going to go over. Not this time, but the next time that we get together as far as identifying what dissolves in water. Let's see here. Okay, now some non-electrolytes. These are things that don't dissolve in water. Or, excuse me, they may dissolve in water, but they don't dissociate. They do not form ions. And so examples of this might be sugar, ethanol, solid sodium chloride, that is to say salt that you didn't put into water. These are non-electrolytes. These do not conduct electricity. Now in our household, one of our favorite pastimes is watching movies. And there's this superhero, I guess, James Bond. And I had this dream once where James Bond is trying to escape from this supervillain. And so there's like the villain's hideout, the super evil lair, because that's what evil people do, is they have like their own private island that is their secret lair. And James Bond has to escape. He has to get away. This is the dream. And so he has to like jump off this dock and somehow get away from this island. And he has a couple of choices. He could go this way and it's fresh water, like Lake Superior, or he could go this way and it's salt water, right? Like the ocean. And there's a thunderstorm happening, because this is my dream, you know, weird stuff like this happens, right? So he has to make a decision, and I'm like, oh, go for the fresh water. Go for the fresh water, because you cannot get, I mean, if lightning strikes, you should be okay, right? Because it doesn't conduct electricity as well. Okay, so now before people decide that, okay, Professor Locken said I can go swimming in a lightning storm as long as I'm not in salt water. Okay, that's not necessarily true. Lightning can still strike you in the water, but fresh water should not conduct electricity as well as would salt water. Acids, what are acids? We've said that acids can form strong electrolytes and weak electrolytes. What are acids? Acids are compounds that produce or make these H3O plus ions. And so an acid is something that gives us this, H3O plus. Now that looks like water, and it is water. Really what it is it's just water with an extra hydrogen. And one way of looking at this is if you have water and you add a hydrogen ion to it, then you end up producing H3O plus. So really anything that can give you this we would consider to be an acid. And some things are better at doing that than others. Now here we have nitric acid, and you notice it has a hydrogen in the front of it. It donates a hydrogen. Here's hydrochloric acid, and again it has the hydrogen in front of it. It donates a hydrogen ion. Now, having pointed that out, does every compound that starts with an H, is it an acid? And the answer is no. But generally with acids, we do put the H's in the front to indicate that they are acids. So it gets a little bit tricky, but some of these you may recognize because you've worked with these before in your general chemistry lab. Nitric acid and hydrochloric acid. Have you worked with nitric acid? Yeah. Now, acids and bases, there are strong acids and there are weak ones. In your textbook, it gives you a list of strong acids. And it says strong acids and the gases that form them. Now the gases that form them, that's not important, but the strong acids over here on the right-hand side, these acids, you should know these acids, like hydrochloric acid, hydrobromic, hydroiodic, sulfuric, nitric. These acids you should know, like maybe make a little note. You're going to need to be able to recognize, okay, these are the strong acids. These are the strong acids. And they all start with a hydrogen in front of them. And then we have some weak ones over here, some common weak acids. And as we look at these common weak acids over here, like acetic acid and carbonic acid and phosphoric acid, these are the weak ones. Now, the hydrosulfuric and phosphoric acids, we don't use that a whole lot, but acetic acid and carbonic acid we do. And so one thing that a student told me once, the way that she remembers which is which, is if an acid has carbon in it, it's not a strong acid, or it would be a weak acid. Now acids come in different varieties. We have acids that are monoprotic, diprotic, and triprotic. Monoprotic. Mono means one, protic means proton. And so this gives us one proton. So a monoprotic acid might be something like hydrochloric acid. And then diprotic means two protons. This would be an acid like sulfuric acid, H2SO4. And then triprotic would be, as you imagine, three protons, and an example of this might be phosphoric acid. And it might go on beyond that, but really the most common ones are going to be monoprotic and diprotic, and it's just the number of protons. And how do we know? Well, if you look at their formulas, you see one hydrogen, two hydrogens, three hydrogens, kind of gives you the impression of the number of protons that it can donate. So now, sulfuric acid. Question for you, is sulfuric acid a strong electrolyte, weak electrolyte, non-electrolyte? Don't say delicious on toast. Sulfuric acid. We just did this today. Is it a strong acid? Nod your head like yes. It's a strong acid. So is it a strong electrolyte? Yes, it's a strong electrolyte. Okay, excellent. Okay, it's like headbanger ball. Okay, we got this. Some strong bases. What are strong bases? Strong bases are things that completely dissociate in water to form ions. And examples of these would be hydroxides of the group 1 elements. So like lithium hydroxide, sodium hydroxide, potassium hydroxide. Okay, so strong bases. Strong bases, these are going to be hydroxides of like lithium, potassium, okay, not hydrogen, sodium. Okay, and then there's some of these group 2 elements, cesium and calcium and strontium and barium. Okay, but really the most common ones that we think of when we think of strong bases is probably sodium hydroxide. That's the one that you might be using in lab. It's kind of a white crystalline substance, and if you leave it out, it tends to absorb water. And then we have some weak bases. Ammonia is a weak base. A weak base is ammonia, NH3 is a weak base. And then amphoteric. Amphoteric just means something that could be either an acid or a base. And water is kind of odd or weird. It's one of those substances that can behave as both an acid and as a base. It's one of those great questions that professors love to throw on tests and quizzes. This is water. Is it an acid? Yes. Is it a base? Yes. It's amphoteric. It could be either acid or a base. Now, theoretically, if I had a beaker of a strong acid and a beaker of a strong base, equal concentrations, and if I mix them together, they should neutralize. Acids and bases neutralize. And I've wanted to try this, but I don't have enough courage. I'll just say I'm not confident about this. I know that this should work. That if I were to take hydrochloric acid, which is a strong acid, take hydrochloric acid, NaOH, hydrochloric acid plus HCl, both of these are aqueous. I react them together. I should end up, let's see, plus, minus, plus, minus. We're going to end up with these pluses flip-flopping like this. And my new substance, my product here, will be H2O and NaCl. Salt water. So both of these, if I drink this, I could die. If I drink that, I could die. Mix them together, it's just salt water, right? It's like Gatorade without the food coloring. It should be okay. As long as I get the concentrations right, I should be able to do this. And I thought, oh, wouldn't that be just a really neat demonstration, right? Like you just grab a student, here, drink this, and they die, right? And another student, and they die. You're like, oh, but I mixed them together. I should double die, right? But I live. Ooh, science. But no, we wouldn't. There's different ways of writing chemical equations, and they tell us different amounts of information. I'm going to show you the three different ways, and you're going to scratch your head, I think, and you're going to go, well, why are we doing this? It seems like a lot of extra work to just figure out what's happening in a chemical equation. And I agree with you. It does seem like a lot of extra work, but it does get us somewhere. It does lead us to something. So I'm going to start out here with our molecular equation. Molecular equation. So this gives us our reactants and our products. Everything in our reactants and our products completely written out, including their states of matter. Now I'm going to use different reactants and products here in my example. Just won't dry fast enough for me. Okay, so I'm going to use sodium sulfate, so NaSO4, sodium sulfate, and this is aqueous. And I'm going to react this with barium hydroxide. Barium hydroxide, and that's also aqueous. And then when they are mixed together, they're going to form something new. Now, to tell what happens, our sodium ions are positive, sulfates are 2-, barium is 2+, hydroxide is a minus. Barium sulfate is going to form a precipitate. It's going to form a solid. How do we know that? We don't know that yet. That comes tomorrow. I'm going to show you the rules for figuring that part out. So this is coming up. Okay. Now we also have to balance this, which means, oh, wait a minute, this didn't have the right formula there. Okay, so I'm going to have to put a 2 here to balance it. Okay, I didn't just add that to balance it. I put that there because that's the correct formula, and you have to have 2 sodiums to balance out the sulfate. I wrote it wrong. I wrote it incorrectly. But in post-editing, when we edit this, I'll make it right, so it'll look really good. Okay, don't worry. Yeah, okay. All right, so there's our molecular equation. Now the overall ionic equation. Overall ionic equation. Overall ionic equation, we're going to take all of these reactants and products and we're going to separate them out into their ions. And so this is going to take a little bit of writing. And so this is, you do kind of the calisthenics sort of thing, and you stretch and make sure you got all your fingers ready to go. Because are you ready for this? Okay, here it comes. We're going to separate all these out, all out into their ions. So that's going to be 2 sodiums. 2Na plus aqueous. Okay, and then we've got a sulfate in there, SO4 2 minus aqueous. And we've got barium, barium 2 plus aqueous. And we've got 2 hydroxides, aqueous. Okay, we can do this, we got this, in the home stretch now. And we've got 2 sodiums, Na plus aqueous, and we've got 2 hydroxides minus aqueous, and we've got barium here and sulfate, BaSO4, solid. And this here, well, yeah, okay, just like that. All right, so now this is all of the ions dissociated, all written out like that, okay? And that's a lot of work. And you're like, why do you do that? Because it's fun? No, because it's leading us somewhere. As we look at this, we've got barium and sulfate. They form a precipitate. So barium here and sulfate here, they connect over here and form a precipitate. As we look here at our sodiums stay the same. So they start out here in aqueous solution, they stay the same over there in our aqueous solution. And so we refer to these as spectator ions. That's a spectator ion. It stays the same on both sides. And over here we've got the same thing with our hydroxide. Our hydroxide and our sodium, these are spectator ions. They don't connect. I'll tell you a stupid story. I went to prom a long time ago. They had different music back then, but it was cool. We had all the cool bands. Okay, right? I saw David Bowie in concert, and y'all can't because he's dead. And I will always have that over you. Okay. Now, at prom, there were people that went to prom but didn't dance. They just kind of stood against the wall, watching other people do stuff at prom. There were other people who went to prom and they hooked up. They danced at the prom. Now, I like to say, I love telling this story. My wife and I went to prom together. Isn't that nice? And we've been married many, many years. The truth is not that nice. We actually went with different people. And we didn't like the people we were with. And then we met at prom. And you're like, oh, isn't that sweet, right? Well, no, actually, we just met at prom. It's like, my date sucks. Yeah, mine does too. Well, let's dance. Okay, we danced. Okay. And then we went our separate ways. We didn't see each other again for years. It was years later we connected. And it was like, hey, you were that dude at prom. And it's like, yeah, you were that dudette, that person at prom, right? Yeah, okay, let's go out and visit and such. And we eventually got married, right? So I love telling the kids, yeah, I went to prom with your mom and we got married, and isn't that sweet and stuff. But it's not, well, like I like to say. I don't let the truth get in the way of a good story. Okay, so the last thing here is our net ionic equation. Our net ionic equation is the reason we wrote all of this. We're just going to take what happens, what actually connects at prom, and put it together. So we have our barium sulfate. Our barium sulfate is what came together. And so what formed the barium sulfate? That was our barium ions and our sulfate ions. So only things that form a precipitate, only things that come together like this, only things that come together is what will end up in our net ionic equation. So we have to write our overall ionic equation in order to identify what are spectator ions, what actually connects, so that way we can write our net ionic equation. However, we haven't gone over how to identify what are the solids. So you might have to leave the net ionic equation part out. You should be able to do the molecular equation, the overall ionic equation. You should be able to do those. You might not be able to put the states of matter in just yet, but that's okay, because the next time we get together, we will go over that. We will have time to cover that.